one very important slide here. Let's think about a grid here, for example, with just some points in a column as an example. And now you measure at one point, x2. There's an airplane going through here. How do you want to change? Let's say the background is 0. I subtract some given field, and you have some measurement. Do you want to just change it in 1 point, and you get a peak here? And if you have a PDE, then you will see waves everywhere in your ordinary or partial differential equation, and it will just dilute, completely destroy your forecast. So you need to adapt the curve in a proper way. And usually, it should not influence just 1 point, because of course there are correlations between different points in your estimate. And so we need to change the fields in a neighborhood, and we need correlations. And these correlations are not fixed. They are dynamic. So here would be a fixed kind of correlation, isotrope, homogeneous. And here's a real correlation telling you how you should distribute your measurement in your field. And if you now have a high-resolution grid, you might have thousands or even millions of points in this area, columns. So it's one measurement touches a lot of grid points immediately. Yeah? And if you run a variational method, minimizing some kind of functional like this one, then the correlation matrices here link all the variables in your state. Yeah? So we need heavy non-local communication to do this. And we need it all the time when we run our algorithms. Very important part. And so 2 slides here to finish this data assimilation part, and then we go on to the criteria. This is our operational data assimilation. It's an LATKF, very similar to what Takemasa is developing here for NICAM. And joined with an ensemble variational method. So this is a minimization type method, but it uses the correlations which come dynamically from this ensemble data assimilation. We are run 40 members. This is what we can afford at the moment. We try to go to 80 at the moment, operationally. And 20-kilometer nest, all of them have a 20-kilometer nest. We have one deterministic high-resolution member of 13 kilometers with a 6.5-kilometer nest, 7 days forecast, or 180 hours. And then we have output for the convective scale, EPS, where we do a similar thing. I'll show you on the next slide. So the EPS system runs the LATKF as well. So we have ensemble data assimilation on all scales, and we try to do it in a very homogeneous way, down all the scales. It's important from my point of view. It's a 4D LATKF, so it's a Cosmo model here. It collects observations during the runs, 1 hourly runs here. Then we have this ensemble type LATKF plus a deterministic part of it. And the Swiss people, by the way, run the deterministic in higher resolution, 1 kilometer resolution over the Alps, and then this one in a 2.2 kilometer resolution in a larger area. So you have the model runs, you have observation operators here, the core EDA components, and then this hybrid ensemble plus deterministic method. One final slide here on the development. If you want to do development with these big systems, you can't just run this all the time because it fills your computer. I mean, if the operational system fills a full computer and you want to run tests basically with another computer, you can just run one test. It's just nonsense. Yeah? So you have to think about the whole development. And what we do is we have a hierarchical strategy of developments. And so this is the pyramid here. I show you step by step. Model runs, data assimilation runs. As single runs, you can start and run in some different resolution, in a smaller resolution. We need training and many experiments. So we then include all the different kind of analysis parts like snow, ice analysis, surface analysis. There are different programs at the moment. We use a file system to do this here because our database is too slow to properly do it. So we call this basic cycling experiment. So we run a lot of these on different levels, 3 days, 1 day, 3 days, 1 month, 4 months, lower resolution, going to higher resolution, first the and var parts only, going to the ensemble parts, because it's so heavy in terms of the load on the databases and on the systems. And then we have a numerical experimental environment system. So this is basically the routine system to run experiments. So when we are done with these, we move to the NUMEX usually, and then we do kind of operational type experiments there, and we just need 1, 2, 3 of them to move it to operations. And then we have a parallel routine running all the time, 24/7, and we have a routine. This is slightly less than the routine, not all the output, not all the runs, but in principle, we can test routine programs, and then, of course, this runs all the time. Verification needs to go through all of it. A lot of tools, a lot of different things you have to do if you test these programs. And when you do the development without all these tools here, you are lost, I would say. So you can't gain the speed to get anywhere. Yeah? So that's crucially important to have something like this. So let me now try to wrap up. I try to basically boil it down to 3 things, I think, which will be very important. So the first one is, traditionally, structure of modern supercomputers is optimized for the throughput of what I would call differential equation-based algorithms. This has been the tradition to do this from the very beginning. So what does it mean? You have this type of stencils on whatever grid you have them, and you try to make your computer as fast as possible to do this type of operations. And it's still good. I mean, we go to higher resolved models, and we have this in all different parts of science. It's in weather and climate, but it's also in neuroscience, it's in biology, and you still need this. I mean, if your computer can't do it, you are lost. So it's a first and will remain a first critical success parameter for all future architectures to do this in a very fast way. And this is what I call basically more this model run. So it's good, but it's only a part of the story. It's not the whole story yet. If you can only do this in a fast way and all the rest is very slow, you get into trouble. So we need further critical success criteria. And as I showed you, the interplay of models with data, and this is both for analyzing the data, and the same holds for genome analysis and others, and understanding massive data sets today with all this exponential increase which we are experiencing, as well as this frequent initialization of models all the time, forecasting with the data assimilation cycle, and what I tried to show you, the adaptation and determination of model errors, biases, model parameters, while you run it step by step to be able to tune the models and prepare them properly. This needs the communication and distribution of large-scale data sets within your system all the time. And it's within your supercomputer part of it, but also beyond. Come to this in the third part. But so here it's the communication issue is crucial. And I just thought, I mean, you all know these type of pictures, of course. And the question is, how do I communicate in my system? And on what level, what hierarchical level do I need the communication? And as I told you, you need, for data assimilation, you need the correlations in your system. So you need the communication. But you don't need global or local. You need some intermediate level potentially. So, and this is kind of tricky. And of course, if you can do this properly, you can be very fast. I mean, there are exponential type of gain of speed by doing this. Everyone knows the Swedish telecommunication network type of speed up of whatever processing. And the same holds for communication. So that's an important part of your computer. And linked to it, education of your developers in whatever type of control language and mechanism you use. If you have your Fortran developers who are not used to it and you have a massive amount of them and your university training and they are not able to really use it and put it into operations, it's not going to work either. So so this part is crucial as well. And we had the discussions between the Swiss people and the German people and all these different parts of the development community. What do you do? Do you go writing your models within a language which can be put onto GPUs immediately? Do you want to do this, or do you want to keep it in a basic Fortran type or C type programming language and then just convert it to something you can use on GPUs? What is so there's a lot of questions here, and I believe you know them, but it's very, very important. And it's highly underestimated in general. So a third point, still 5 minutes, 6 minutes to go. I showed you the whole chain here. So traditionally, what do? We start executing a program by transferring a massive amount of data from a hard drive or a database into the main memory of the computer. And then we do the calculations in a fast way, because this is the computer is built for. And at some point, we save it on hard drive, or usually on hard drive to a database. And that's it. And then there's post-processing coming, and visualization tools. They read the data from the database, again, put them on some other hard drive. And then they do the visualization and the post-processing. They pull out a massive amount of data, again, from the hard drive. And we are dead here, actually, just from experience at the moment. We have a supercomputing center, and if we want to just pull our ensemble out of our database, it never comes. So whenever we have put it into the database, it's storing it there forever, but we can never, we can get it back, but it takes ages, and it's impossible to use. So basically, if you want to use your data and you don't have the communication running in a proper way, it basically blocks your whole application process. So with temporally and spatially dense observations and high-resolution models and rapid assimilation and forecasting systems, the whole chain breaks down. Just not going to work anymore. And the chain needs to be redesigned. So I put this here for the chain. I mean, here you have the app data, which is on the web for 5 million users in Germany. This is our model when all the programs run in different strands here for the regional models and the global models. And here's all the data coming in. And even the data, I mean, EUMETSAT is basically thinking about not storing the data anymore because it's so massive. They can't get it down from the satellites. So they convert it with some PCA, some transform on the satellites, pulling out the main information, pulling only the information down, and then we put the same conversion in, either the inverse conversion into our system, or we use the converted data. And this is called PC principal components for the satellite data. So we, on all levels of the chain, we are thinking about how to deal with the massive information we have. And here, so it has further strong impacts on the resilience and error tolerance of the full system. And also, I said, it depends on the past. I explained the spin-up processes. So if you lose a part of your system, your spin-up is gone. You start from scratch. And we can show that the forecast quality goes down heavily if you do this. So if you have errors in your system and you have more and more processors, you have more and more errors on different levels, and you lose part of your system, you might be in trouble with your quality because it's going down all the time. So the third critical success parameter is this whole mechanism dealing with all the communication and the data on different levels. And we have, and this is what leads me to the last, so we need hierarchical security levels in the HPC systems, and we really need to think about what we need to keep on what level for what purpose. So this is really, you need to talk between applications and the computer designers, otherwise you get nowhere. It's very difficult to do this at the moment in a general way. And there's a further part, and it brings me to the last part of my talk. Some slides only. Here I have just some diagrams, which I don't want to explain in detail, but basically we are running HPC on the Cray supercomputer, and we are running fast nowcasting algorithms on a level 2 server, fast server. And now we want to intertwine the two. So we want to pull information from the HPC part to the nowcasting part and vice versa. But they are on two different worlds. Two different programming languages, two different communities, two different server worlds, different contracts. We are not even allowed to just take one part of the servers and plug it into the other part, because we have legal contracts with some vendors here and some vendors there, and it's just impossible. So we even have to think about the legal aspects of all of this before we buy anything. And we can't just transfer the data. It's just too much. It's not going to work. It takes too long. If we need it every 5 minutes and it takes us an hour to transfer, it's just not going to work. And this is one part. And the second part here is that if we run something every half an hour, how do we keep it stable if something breaks? So we have this analysis cycle, our traditional analysis cycle here, and we have the rapid analysis cycles here with the forecast. And basically, we need to make sure if something fails, and that happens all the time somewhere, here we still have some time to repeat it and do it again. Here we are lost. So if we depend on this here, we are lost all the time. So we need to design the whole system in a way that this error tolerance is there, not only on the hardware level, but also on the whole system level. Yeah. So that brings me to the last 3 slides here. We have a big project which is called a nowcasting and NWP integration, called Symphony now, official name, Seamless Integrated Forecasting System. And it basically, the main idea can be communicated with these 2 images. This is the nowcasting, this is the model. They're kind of similar, but not the same. So the weather forecasting people said, generate a project, brings this together. We want a seamless forecast. We don't want to break after 2 hours. Yeah, moving from one picture to the other. This is the easy version of it. And it's the Symphony project. And so we have a nowcasting ensemble prediction system. We are working towards a high resolution ensemble prediction system run every hour with forecasts, and this traditional EPS system short range NWP, which is run already every 3 hours. And we need all the post-processing, and we need all the cycling environments and all the setup for this. And if you put it, I think 1-2 minutes I have, so 2 slides left, or 3 slides. The whole thing is, first you have your nowcasting algorithms with your forecast, 5 minutes. Here you have your NWP, 1 hour. And then you have all different kinds of links between the 2 and combined products for forecasters. And we have a project with approximately 15 researchers working on this in the different parts, talking basically on a daily basis how to bring this together. And I'll give a detailed talk on this on Friday here in the Recon seminar. Yeah, so I have an hour then on this. Just a 2 final slides about some ongoing research projects here. What happens at the moment is that, for example, the car industries come and say, we want real-time weather in our cars. We want to know what's around the next corner for our autonomous driving and our supported driving, and our premium cars 3 years from now will have it all. And you help us. So you have your weather model on the supercomputer, and we give you all the information from the cars, all the measurements, and the car is full of equipment, even now. And they are saying, tell us what to put in, then tell us how to move it to your system. You give us back the weather every minute, basically, and then we, on a 1 kilometer resolution, or even 500 meters over Germany, yeah, and it's much higher than all our high resolution models. And on a 1 minute, 5 minute resolution at least. So, so we have all the sensors in the cars, nowcasting and NWP. We need real-time weather for the next 5 to 60 minutes, and they want to know what's going on and where to drive and where the showers come and the high precipitation and where they should direct their people. And basically, they will have servers in the cars. This is ongoing technology already with some demo systems at the moment, but it's supposed to come very soon. And so we made a project where we update parts of our state, not the full state. So we are going slightly different to the tests which are being done here with a 30-second fast cycle. We think we can't do this operationally at the moment, so we need to come with some solution, and the solution is this one. So we update parts of the system for the next 5 to 60 minutes. Basically, yes, and I show you results on Friday. So we have first tests, it works. And basically, we work on the high-resolution ensemble forecast, and we change it by an ensemble data assimilation step for the future as well, for the next 60 minutes. And we first test show that this works for our real system. And it's very fast. It just takes you a minute on the high-performance computers. So this was my thing. Summary. 3 critical success parameters for the future systems. Throughput remains number one. Non-local communication on different layers is number 2. Very important, underestimated. And the development of resilient and very modular complete system structures, which includes a whole line of transfer of information until you have information at the customer is the third one, which will be more and more important in the future. And it will be an exciting time with emerging structures, both on the software and the hardware side, I believe. So thank you very much.